Hello, everyone. It's Michael Shermer, and it's time for another episode of The Michael Shermer Show. This one is brought to you by Wondrium, a series of college-level audio and video courses and documentary films and series produced and distributed by The Teaching Company. Wondrium brings you engaging educational content through short-form videos, long-form courses, my favorites, tutorials, how-to lessons, travelogues, documentaries, and more, covering every topic you've ever wondered about, and many, many more you've never even thought you'd wonder about. For example, here's one I'm going to take this week. Again, the app is right on the phone. You just tap it, open it up, and it gives you a whole series of courses and tutorials and films and things you can watch or listen to. This one's called The U.S. Constitution Through History. This is 24 30-minute lectures, which I always listen to at 1.2 or 1.3 speed, depending on the lecture. America's Founding Ideas, Failures of Early American Governments, Dilemmas of the Constitutional Convention, Ratification of the Constitution, the Bill of Rights, the First Federal Powers, Hamilton's Bank. And this goes on, and I'm not going to read all 24 of these, but you get the idea. The nice thing about these, you start a lecture and it remembers where you're located in the lecture, such that if you stop and come back, it's right there. Or if you skip to another lecture, maybe you even change courses, literally, and then you come back to this course, it picks up right where you left off. So check it out. Go to wondrium.com/Shermer to get 50% off the first 3 months of Wondrium. It's a subscription service, so that's half off the first quarterly plan, 50% off the first 3 months. It's a great deal. Wondrium.com/Shermer, WONDRIUM.com/Shermer, SHERMER. Check it out, Wondrium.com/Shermer. Get your 50% off those first 3 months of Wondrium. It's a great way to spend your time. All right. This one is brought to you by Wren, W-R-E-N, Wren. Wren is a startup that's making it easy for all of us to work toward making a difference in the coming climate crisis. I don't think it's an existential crisis, as you've heard me say here. I think it's the kind of problem that we can solve in the long run if we all do just a little bit of changes in our actions. And here with Wren, they're not talking about, you should use less carbon, make a lower carbon footprint. No, they will calculate for you what your carbon footprint is, information you give them, obviously, and then they will plant trees. And in your name, to counter, well, you get involved in all this, but they plant the trees for you and do other things that help sequester CO2 gases and in the long run, lower the average global temperature. In the long run, again, this is a collective action problem. No one of us can make a difference, much of a difference at all, but collectively, if enough of us do it, and particularly if we get momentum, then we can make a change. And again, I think in the coming years, decades, centuries, it'll be fine. We will recover from this. We will solve this problem just like we did the ozone hole in the ozone problem. And we did that through collective action against that, and that's what Wren wants you to do. So here's the deal. If you go to wren.co/Shermer, WREN.co/Shermer, they will plant 10 extra trees in your name. Now, that's pretty cool. I did it. I think it's cool. I calculated my carbon footprint and so on. And if enough of us do it, it will make a difference. So check it out. That's WREN.co/Shermer, Wren.co/Shermer, and you'll be on your way. It's a cool thing. Check it out. Thank you to that company for supporting this podcast. As you know, we don't have a lot of advertisers on here, and I would only have people that are doing something that we support and that I personally support. Thanks for listening. Here's our episode. My guest today is Tim Palmer. He is a Royal Society research professor in the Department of Physics at the University of Oxford. He pioneered the development of operational ensemble weather and climate forecasting, and in 2007, he was formally recognized as having contributed to the Intergovernmental Panel on Climate Change's Nobel Peace Prize. Palmer is a Commander of the British Empire, a CBE, which is pretty cool, and a Fellow of the Royal Society, FRS. and the National Academy of Sciences, and a recipient of the Institute of Physics Dirac Gold Medal. He lives near Oxford. Tim, nice to see you. Thanks for coming on the show.
Hi, thank you. Great pleasure.
You can imagine I love the title of your book. This is the book we're discussing today, The Primacy of Doubt, given in as much as that I publish a magazine called Skeptic and might as well be called Doubt. The subtitle is From Quantum Physics to Climate Change, How the Science of Uncertainty Can Help Us Understand Our Chaotic World. We'll be releasing this conversation the week this book comes out. So congratulations. I love the book. It was a really fun, interesting read, well written. Anybody can understand it, even though there's some technical science in it, but that's a sign of good science writing, in my opinion. And so let me just open with the epigrams here you have from Richard Feynman, in which you write, quoting him, "Our freedom to doubt was born of a struggle against authority in the early days of science. It was a very deep and strong struggle. Permit us to question, to doubt, that's all, not to be sure." So I gathered Feynman is something of a role model for you, or hero, or just somebody to admire.
Yeah, absolutely. I mean, Feynman's a role model, I think, for pretty much any physicist. My background was in physics and theoretical physics, so he figured very strongly in my education. And maybe I could add the second quote in that thing, which is that the actual phrase, the primacy of doubt, came from a quote by James Glick, who did a wonderful biography of Feynman. And Glick says, Feynman believed in the primacy of doubt, not as a blemish on our ability to know, but as the essence of knowing. And I kind of find that a very kind of profound statement, that, what characterizes us humans and our knowledge and our ability to think and reason and so on is intimately connected to the fact that we are infallible, we make mistakes. We're not computers that just run the same old programs over and over again, getting the same answers. So there's something profound about the human condition and the notion of uncertainty or doubt.
I want to spend some time on that, but first I'm going to do a slight detour from your first page of your author's note to give some biographical background, and then I'm going to seg into how you ended up doing what you're doing as an example of chance and contingency in how lives turn out. So you'll see where I'm going with this. So here's quoting from you. "I studied for a PhD in the 1970s researching Einstein's theory of general relativity. Einstein had become a hero of mine by the time I was a teenager. I was lucky. The 1970s were considered to have been a golden age for general relativity theory. At the first scientific conference I ever attended in 1974, I literally heard Stephen Hawking, he hadn't lost his voice, announce his most important and famous result, that black holes aren't truly black, but radiate quantum particles." That's Hawking radiation, right? So first of all, what was that? What was that? Well, let me continue, because you end up with a great story here. My research supervisor, Dennis Sciama, Hawking's PhD supervisor some years earlier, was ecstatic about this result. Sciama was optimistic that we were on the verge of understanding how to unify Einstein's theory of general relativity with quantum mechanics, the theory that successfully describes atoms and elementary particles. There were problems, however. One problem which frustrated Sciama was that Hawking's calculations were a little arcane. Sciama was convinced that there must be a more physically transparent way of deriving such an important result. He started to look at alternative ideas based on concepts from a field of physics called non-equilibrium thermodynamics. Sciama asked me to look at what is called the principle of maximum entropy production, something I hadn't heard at the time. Toward the end of my PhD research, I had become an expert on black holes and was successful in securing a postdoctoral position in Hawking's group at Cambridge. All seemed set for a career as a theoretical gravitational physicist. Indeed, why would you want to do anything else? I mean, you're at the peak there, and yet you ended up doing something completely different.
Yeah, it's a good question, and I often, actually, I don't often, but people often say to me, what would your career have been like had you stayed? I think there were two things. One is that, when you, let me tell you a story. I used to very frequently, at parties in Oxford, people would ask me, some really attractive young lady would come up and ask me what I would do, and I would say black holes. And she'd go, wow, that's fantastic. Wow, that's incredible. Black holes. Wow, that's incredible. Just tell me a bit more about what you do. So, okay, so you want to know a bit more detail? Well, I research into gravitational energy momentum from black holes, and how I'm looking for mathematical solutions for the quasi-locality problem, which involves looking at tensors over the tangent bundle to phase space and mappings down onto space. Anyway, so I've got half of these sentences, and you can see, oh dear, starting to very rapidly lose interest. So the point is that when you're doing research, you're really doing kind of nitty-gritty mathematical details on probably kind of really infinitesimally small parts of a theory. And at some stage you ask yourself, well, am I going to crack the really big problem, with what I'm doing? Because after all, what I'm doing affects nobody. It's not really of any great service to humankind. I'm doing this just for the sort of hell of it, if you like, in some sense, advance physics. So I better advance physics in a pretty fundamental way, I guess, was my thinking. And the more I thought about what I was doing at a very, very detailed technical level, I was kind of decided, I was just making small inroads into a very big problem that I wasn't likely to solve. And the big problem, which is actually still a problem to this day, is how to reconcile quantum mechanics and gravitation. It sounds fascinating, but unless you have some very specific ideas, you're either following along, dotting I's and crossing T's from some other person's work, or you have your own idea about how to make progress. And at the time, I didn't have any great ideas. So I got more and more thinking, well, maybe I should spend most of my career at least doing stuff that is more relevant and hopefully useful to my fellow human beings. And that kind of led me ultimately to I have to say, my parents' dismay. I mean, they obviously wanted me to go to Cambridge and work with Hawking and so on. But in the end, I decided to do something different. And all I can say is it's worked out really well. I actually continue to in what spare time I have, I continue to probe some of these issues about quantum mechanics. But fundamentally, most of my kind of active career has been much more in the climate and weather science, which I believe I have made some impacts on how we perceive weather and climate. So I think it's been a good decision, but of course it's a counterfactual to know what the alternative would have been like. But my gut feeling is it wouldn't have been as good.
Interesting, yeah. So give us some sense of, before we dive into all that research, what was it like to work with Stephen Hawking? What was he like as a person, and how did you work as his condition worsened?
Well, no, I mean, Stephen was in Cambridge, and my Dennis Shermer, who supervised me, was Stephen's supervisor, was based in Oxford. Dennis had been in Cambridge, so when he supervised Stephen as a PhD student, he was in Cambridge, but he moved to Oxford in the early 70s. Now, my biggest two influences were Dennis Shermer himself, but also Roger Penrose, who had moved, again, very recently from Birkbeck College in London to Oxford, to the Mathematics Institute in Oxford in the early 70s. Roger was a phenomenal person, well, still is, of course. He's won a Nobel Prize a couple of years ago and still very active in his 90s. But he was, he was a kind of Richard Feynman of general relativity. So as Richard Feynman is to high energy particle physics, so Roger Penrose is to, and certainly was in those days, to general relativity, and in particular black hole physics and all that sort of stuff. And I have to say, I kind of probably, some of my skepticism about traditional quantum mechanics and quantum field theory and stuff like that, which goes into standard particle physics, probably came from interacting with Roger Penrose in those days. Roger's carried on the, I guess Roger has carried on the tradition from Einstein, if you like, of being somewhat skeptical about quantum mechanics, even though experimentally it seems to be a very accurate theory. So I didn't have much interaction with Stephen during my PhD. I met him a few times. Of course, soon after I heard him speak. I mean, it was difficult. He'd already almost lost his voice when he gave that talk in the conference I went to, but he hadn't quite lost it. But he was, it was difficult to, his speaking was difficult. So it was difficult to understand him, and it became increasingly difficult to communicate with him. So I would say the communications I had with Stephen were pretty limited, unfortunately. But, if I had gone to Cambridge, they would have obviously improved, but that didn't happen.
Mm-hmm. Yeah. Yeah, just because I'm curious, what's the problem to be solved? Why does quantum physics need to be righted with general relativity? Why can't there just be two different physics for two different levels and just leave it at that?
Well, because we think there is a domain where the two will overlap. So, for example, we can currently send, I mean, the sort of iconic experiment that demonstrates the quantum nature of particles is what's called the two-slit experiment. So the two-slit experiment, was originally done for light, beams of light in the 19th century by Thomas Young. So you take a beam of light and you pass it through two slits, and you get this kind of funny, what's called diffraction pattern in a screen behind the two slits, where you get regions of the screen which are very light, and then other regions which are dark. And the explanation is when you have light waves, the waves are kind of interfering to create regions of darkness. Now, the extraordinary thing is that so in the 20th century, it was realized you could send particles of light through one at a time. These are photons. And again, the pattern, you send them through these two slits, and this pattern of light and dark kind of emerges, even though the particles go through this one slit or the other, one at a time. So it's a real mystery to know how, even to this day, it's still a mystery as to why this interference pattern builds up. But that's a quantum phenomenon. Now, over the years, people have sent heavier and heavier particles. So photons, yes, do that. You can do it with electrons. Then you can do it with individual atoms. And now people are even talking about, sending little sort of bacteria through slits and getting interference patterns.
Whoa.
So then the question arises, what happens when you send particles that are so massive that you can detect their gravitation, their own self-gravitation? And this is something we can't quite do yet experimentally, but we'll soon be able to, I think, in a matter of years. And it's really an important question as to whether sort of particles whose gravity you can detect will still show this interference phenomenon or not. So whether it does or it doesn't means that, for what it's worth, my betting is that once you detect the gravitation of a particle, you won't see this interference effect. But other people will say otherwise. But basically, that is testing a kind of a regime in physics where both quantum mechanics and gravity are simultaneously important. And so we need a theory to describe that situation. What the theory is, as I say, is open for grabs. And then, in the whole kind of nature, in a more esoteric way, the nature of the Big Bang, the beginning of the universe, and what goes on in the center of black holes it will be impossible to properly understand without having this combined understanding of gravity and quantum mechanics in a single theory together. So there are good reasons why we need this, but it's absolutely the holy grail in theoretical physics. And as I say, my supervisor, when Hawking announced his result, he thought, oh well, we'll have solved this problem within 2 or 3 years. But over 50 years later, basically, we're still struggling, and the solutions still, I don't think, in sight either.
I'm not sure if this is applicable, but jumping ahead to your chapter on consciousness, you discuss, Roger, Penrose and Stuart Hameroff's theory of consciousness. And I should note parenthetically, there's like 27 different theories that are floating around out there. So I think we're a long ways from any one of them being obviously right. But their idea that inside neurons are these little microtubules that are like scaffolding that hold the cell together. And inside the microtubules, there's these little quantum effects that can be measured. And that their idea is that, if I get this straight, there's kind of a correlation between the neurons in a brain that the wave function is collapsing in some kind of synchronized way. And out of that, you will get this kind of consciousness, whatever we mean by that, sort of aware of being aware in some level, something like that. But then the counter to that, when that first came out, was that, well, those quantum effects apply at the subatomic level, but neurons fire at a molecular size level. These are, massive, chemical molecules going between these neurons and these synaptic gaps and operating like a lock and key molecules and so on, and that would wash out that. Now, last time I talked to Stuart about this, he said, no, there's quantum effects at the macro level now and so on. And I haven't followed closely that research, but so kind of walk us through some of that.
Well, I think you're right to say that this is still a very uncertain area of science, both from, physically exactly how quantum mechanics operates in the brain, and secondly, whether quantum processes are fundamental for consciousness. I personally am personally, I do think quantum processes are important in the brain. I'll give you an example of this in just a second. But I also I'm inclined to Penrose's view, because his ideas about consciousness were very much motivated by the question of whether computers, can really understand things in the way we understand things. And I still think, the example he used in his original book, The Emperor's New Mind, of what's called Girdle's theorem, which basically says there are aspects of mathematics that, can't be described with algorithms. So, there are things that are true, but are not sort of provably true with an algorithm. Now, a computer, by definition, is something that works using an algorithm. So a computer, by definition, cannot understand this kind of notion of Gödel's theorem, whereas we humans can understand it. I mean, if you read through it, you can follow each step, and you say, okay, yeah, I get all that. So Penrose's point is to say, well, if that's true, there must be something that the human brain is doing which is not like just an algorithm that a computer runs on. So I find that actually, although I know some people are not convinced, but I find that a fairly sort of powerful, generic kind of idea. Now, one of the things which has interested me over the years, because I use in my professional climate work, I use computers a lot, and really, really big computers, like the biggest computers that there are in the world. And in fact, I spend a lot of my time advocating for the fact that in climate science we need even bigger computers than when we can get at the moment. If we really want to get down to the nitty-gritty of climate change, we need much bigger computers, or access to much bigger computers. But there's a really interesting kind of anomaly between the human brain and a computer, which is that computers are unbelievably energy intensive. So these computers, which do all these calculations, are consuming tens of megawatts of power. And most of that power is actually used to move data around from one bit of a computer to another. Now, in the human brain, we actually, the optical nerves are actually transporting pretty much as much data into the brain as a big supercomputer moves around. And it processes all that data from the outside world, tries to make sense of what we perceive and so on. But it does it all on 20 watts, so 6 orders of magnitude less than a computer does. So, supercomputer. So I think that's a kind of, I'm totally convinced that, there are some big clues in that, trying to just emulate the brain on a supercomputer is kind of missing the point, which is that it does it on 20 watts on a light bulb, what a light bulb takes to light. Now, so I've been certainly interested in trying to understand why the brain does what it does on such a low amount of energy. And I came across a really interesting paper by some physicists and neuroscientists from Austria. Gustav Bernreuter is one of them, who's somebody I've met a couple of times now. And what they have realized is that you talk about neurons and sending signals along these axons of neurons, so these long sort of wires, if you like. Now, the point is that the signals have to be boosted every short distance, because otherwise they would just dissipate in the sort of noisy environment. And they do that with kind of what you might call protein transistors. That's the analogy of a transistor amplifying a signal, but it's done with these what are basically ion channels. So electrically charged atoms, are fed through the walls of neurons in a controlled way, which boosts the signal that propagates along the neuron. Now, what these scientists have realized is that if you did this, if these protein transistors were acting purely in a classical way, so non-quantum way, the amount of energy you would need to do the signal boosting would just be more than is available by a long way. And what they have realized is that it's actually a very quantum mechanical process which allows these protein transistors to operate. So here, quantum mechanics is acting in a way to reduce the energy demand on the brain. So it's one of and there may well be other examples of how quantum mechanics allows the brain to do things which at a classical level would be impossible or just take too much energy. Now, I don't know whether, Stuart Hameroff and Roger Penrose's microtubules would actually come under that category, that they're, from an energetic point of view, they're something where quantum physics can do things much more energetically efficiently than classical physics. But certainly this whole area of neuron propagation, I think, is a great example of where quantum mechanics can step in and say, I can do this much cheaper than you could ever do with classical physics. And this has got to be surely a kind of an important message for, building computers which make much more efficient use of energy, which at the moment we don't do. So there's lots of uncertainties here, but I do think that's an example of where quantum mechanics probably does play a really important role in the brain, and I think, this is another issue, but I do think it's something I discuss in the book. We may not want to go into details now, but the whole question of free will and consciousness, I think it actually is bound up with the role that quantum mechanics plays in the brain.
Well, we can get into it because this is super interesting stuff. I've had most of the big consciousness people on the show, Matthew Cobb and Christoph Koch and Neil Seth and Jeffrey Goff and John Joe McFadden. They've all presented their ideas. I guess my one beef I have is that this often turns on language. My favorite science cartoon is Sidney Harris's cartoon with the two mathematicians at the chalkboard and with the complex equations, and then in the middle he says, and then a miracle happens, and the other one says, I think you need to be more explicit here in step 2. I often feel like and then the microtubules and the wave function, and then consciousness, and then the waves, the kind of electromagnetic waves that the EEG is picking up, and then consciousness. To me, it often feels like, and then a miracle or emergence. Complexity theory, emergence, and then emergence happens and consciousness. To me, it often feels like, and then a miracle happened.
Right. Well, I understand that. And, so, I discuss consciousness a little bit, and I'll give you my definition of consciousness in a second. But let me precede it with saying something about free will. And I've got interest. I mean, I'm interested in free will because it appears. I say appears because there's some controversy about this, but in standard. So I need to backtrack. So in the book, I discuss a lot about whether the uncertainty principle in quantum mechanics, which anyone who knows anything about quantum mechanics knows this thing called the Heisenberg uncertainty principle, which is really, really difficult to understand, because normally when we think about uncertainty, for example, in weather forecasting is an example of a chaotic system, and a chaotic system is one where very small uncertainties in the initial conditions for a weather forecast can lead to a very different prediction of weather. So we could say that we are uncertain about what the weather's going to be like in a couple of weeks' time, because we humans don't have perfect knowledge of today's weather. We can't measure it absolutely everywhere, all the little whirls and eddies and so on. So uncertainty is in that context, and in most contexts in which people use the word, kind of reflects what would be called a kind of epistemic uncertainty. In other words, an uncertainty that that we have about the system we're trying to predict or understand. The problem is in quantum mechanics, and I have to say Heisenberg himself, when he wrote some of his first kind of expository articles about the uncertainty principle, he actually tried to explain it in those terms. It's sort of, we can't kind of measure stuff arbitrarily accurately. And Niels Bohr, who was the one of the great grandfathers, pioneers of quantum mechanics, took Heisenberg to task. He said, no, this is not right. Whatever uncertainty is in quantum mechanics is different. It's the word philosophers would use is ontological. There's something inherently uncertain in the equations of quantum mechanics. So that's the standard view, which personally I don't actually believe, but that's a very controversial view. So So I go into quite a lot in the book about. So what is the if you had to say one reason why people don't think that uncertainty is epistemic and is more ontological, they would probably cite something called Bell's theorem or Bell's inequality, which is a kind of an experimental test which seems to suggest that there is no kind of definite, that quantum reality is not definite. It's something sort of indeterministic and sort of, I don't know. It's difficult to use words actually here because it doesn't it doesn't match with anything that we sort of understand. So in my book, I go into Bell's theorem quite a bit. Now, Bell's theorem, as it's usually phrased, so I'm coming around to your question. Bell's theorem, as it's usually phrased, involves the issue of free will. So in Bell's theorem, you imagine experimenters who measure, they just do simple measurements on particles, like measuring their spin. But an important ingredient in Bell's theorem is that although an experimenter actually measured the spin of a particle in a certain direction or with their apparatus oriented in a certain way, they could have measured the spin in a different way. So in other words, the standard way in which Bell's theorem, which seems to suggest quantum uncertainty is ontological, requires this notion of it requires this notion of counterfactual worlds where the experimenter did other than what they actually did. And I have been using ideas from chaos theory, and in particular the mathematics of the geometry of chaos. So underpinning chaos is this wonderful, wonderfully beautiful, fantastically just incredible fractal geometry. And fractals have gaps. So if you look at a fractal, it's always got little gaps. And the gaps, you zoom in and there are gaps within the gaps and so on. They get smaller and smaller, but they're always there. And my claim is that some of these crucial counterfactual experiments correspond to points that lie in the gaps in these fractals. So if your theory is based on these fractals, then these counterfactual experiments would actually be disallowed by this theory. And so this actually provides a way of getting around this Bell's theorem. However, so we're coming to your point now. People say, well, yeah, but I do have free will. I could have done this experiment. That's what sort of a typical kind of reaction. And so, if it raises the question, well, first of all, raises the question, what is free will? But a question which people don't ask very much, and there's something I've kind of dwelt on in my book, is why do we humans feel so very viscerally and kind of almost, will thump our fists on the table to assert this point that we have free will? What is it that actually makes it such a, I'm sure a computer doesn't have this feeling of free will. So what is it that makes us feel we have free will? So this is where I think, again, quantum mechanics in the brain could be playing a role. So this is my hypothesis that, because I do actually believe that ultimately the laws of physics are deterministic. So there's no kind of randomness in the equations of physics, ultimately, that things are deterministic. But you see, so the question is, what distinguishes quantum mechanics from ordinary classical mechanics? And this is where this idea of, this is going to sound a little bit kind of weird perhaps, but I can assure you there is mathematics that will sort of back this up, but we don't want to go into it now. But the idea is that I'd mentioned these kind of fractal attractors. The idea is that quantum mechanics feels, so you see, we can think of our world as the world evolving that we perceive to be a particular sort of solution of the equations of physics. But there are nearby solutions in some kind of more abstract solution space, if you like, with slightly different initial conditions. And quantum mechanics kind of feels these neighboring solutions in a way which classical physics doesn't. It kind of feels the geometry of this fractal attractor. It can sense, if you like, little neighborhoods of this geometry. And my feeling is that what we think of as free will is a very sort of weak and imprecise perception of these neighboring solutions, which we would interpret as worlds where we did otherwise. So my belief is our really strong visceral feeling about free will comes from this notion of sort of alternative solutions in this abstract solution space. All right, okay, so then I got thinking about, so I'm going to come to consciousness because that links to consciousness.
Okay, but Tim, let's halt for just a second because there's a lot of jargon on there I want to unpack. And this could be the core question for the entire book, that is, to what extent is uncertainty built into the system itself and is not just a limitation of our knowledge? So the latter would be epistemic, the former would be ontological. So here I have, from my coin collection, an 1883 silver dollar, 1883 silver dollar. It says, "In God We Trust" on there. So they've been putting that on the coin since the 1800s. So if I flip the coin and just do my little flip here and okay, it's tails. All right. So I flip it again, boom. And this time it's tails. So 2 in a row. And so I do this 10 times or 100 times. And so we know that I would say, well, I got a 50-50 chance because it's not a rigged coin. But that's only because I just don't know all the particles in the wind currents in my room here or whatever. Exactly. Are you saying that if Laplace's demon was real, or it was the equivalent of a magician that is doing a trick and so knows 100% what the outcome is going to be, or God is, knows, is omniscient and can tell, or is it that even with all the knowledge we have, you still cannot predict with 100% certainty the flip of the coin because of something built into the physical system itself?
Well, okay. So what if I wear my conventional physics hat? If you ask me that question, to me, a physicist, and I'm a representative of the conventional physics community. So I'm giving you the kind of conventional answer.
Yeah.
Then I would say that in quantum mechanics, so if you were flipping, if you like, an atom, if you like, or an electron or something, if you're doing the equivalent of this coin flip to a quantum mechanical system, like an electron or an atom, then the uncertainty would not be because you didn't know something about the atom. It would be because there is something inherently uncertain and indeterministic about the equations for the quantum system. So I have to be slightly technical, because when you do two things. When you do the equivalent of a coin flip to an atom, you flip the atom in some sense, but then you have to look at it to measure. You actually have to see whether it's kind of up or down, if you like, heads or tails, quantum heads or quantum tails. And the traditional view is that the actual process of looking to see whether it's up or down, which is called measurement, introduces some inherently uncertain, indeterministic kind of physics. So that's the standard. So that is different to the epistemic uncertainty, where it's just something about the coin that you don't know. Now, Einstein famously thought that was bunk, because his very famous statement, "God does not play dice," was exactly, making the point that that's ridiculous. I mean, how can it be that nature has indeterministic equations? It doesn't make sense to him. And of course, Schrödinger thought it was nonsense as well. Schrödinger with Heisenberg, was one of the two founding fathers for the basic laws of quantum mechanics that we now use every day in many different areas of physics. And his famous cat is an example of that. So the cat, the cat's in the box. You have a little atom which may or may not decay, has a probability of decaying. And again, quantum mechanically, you have to say, after, say, 10 minutes, there's the atom is like half decayed and half not decayed in some weird sense. But the idea is if it has decayed, it breaks a capsule of cyanide and kills the cat. So then you say, well, what state's the cat in? And the state of the cat, it's not just that you don't know whether the cat's alive or dead. You open a box and you can see whether it's alive or dead. But quantum mechanics says inside that box, before you've looked at it, the cat is neither alive nor dead. There's some inherent uncertainty about the aliveness or deadness of the cat. Now, Schrödinger introduced that example not to say that cats are both alive and dead at the same time, but because that's a completely daft idea. It's just stupid. And he wanted really to make the point that there's something wrong with quantum mechanics. Even though he was one of the fathers of quantum mechanics, he realized there was something wrong with it. And so in the book, I try to develop ideas which might take us back. And I'm not in any way claiming I have a complete theory. I have a theory to the extent that I have papers published in the peer-reviewed literature, and I certainly don't go into any technical details in the book. But I'm trying to show a path, if you like, which might take us back towards a more kind of sensible, I suppose, theory of quantum physics, where uncertainty is again epistemic. So the fact that we don't know whether the cat is alive or dead It's just because we don't know all the details about how that atom decayed. But sure enough, inside the box, the cat would be alive or would be dead. So that's so that I'm just, I try to go so that, and then that leads to the free will. And then if we have a minute, we'll talk about consciousness.
Yeah, let's stay on free will for a minute, because first, as you know, Dan Dennett argued that quantum uncertainty doesn't give you free will because it just throws an element of randomness into the machine.
Absolutely.
And no one's making any choice.
Absolutely. Yeah. So if you just add, that's a really important point. If you just say, oh, there's something indeterministic about quantum mechanics, then all that will do for you is that, every time you're making a decision, it's like, just something random goes into your head, and that's what causes you to make a decision. But that's clearly not how we make decisions most of the time. We think through things and, analyze things carefully. And free will that's not what free will is. So I totally agree with Dennett on that point.
It seems to turn very much on the question, could you have done otherwise? So if we have these thought experiments like, you rewound the tape and played it again, well, if it's a read-only memory tape and everything is just rerun exactly as it was, well, yeah, you'd have to do exactly what you did because it's just basically a movie of what happened. But so the question then seems to be, if you could emulate the tape, say tomorrow, where it's pretty close to what happened yesterday, could you have done otherwise? And so if I'm following you, I think you're saying you could, because particularly if you know the causal factors operating on you, and you know that yesterday this happened, and so tomorrow I'm going to avoid going there or stepping left, and I'll go right instead of left or whatever, because you're aware of what happened. And the universe can never be completely perfectly replicated from one day to the next unless, so here's a key question, the universe is predetermined. So this block universe idea, or there's a God outside of it that knows every particle and already knows what happened next week, just that we don't know. So take it from there.
Right. Well, I think you've absolutely hit the nail on the head by saying this whole thing hinges around, could we have done otherwise? So let's just analyze that a little bit more carefully. So as you say, you come out of a shop, and there's a cyclist on the pavement, and the cyclist collides with you, and you're carted off to hospital with a broken leg or something, and that ruins your life for the next year or so. And you say to yourself, oh, if only I had looked, round, I would have seen that bicycle and I would have avoided it. So what you have to do then is you go back to that moment you're leaving the shop, and you're imagining a world in which everything is the same. The bicycle is still, the cyclist is just riding on the did I use the word pavement? I have to be careful about British English here. Pavement means sidewalk, I think, in America.
Yeah,
so the cyclist on the sidewalk, yeah. What we would call the pavement, which I think you mean the road.
He should
anyway,
not be there. First of all, he should not be
there.
He
shouldn't be there. That's the main point. He shouldn't have been there. But so anyway, but the point is, you wind you're lying in bed in hospital, and you're winding the clock back to that moment you left the shop, and you say, okay, I'm going to keep everything in the universe fixed. The moons of Jupiter are where they are. The moon is where it is. The cyclist is where he is, and everybody else is where he is. But I do one small thing differently. I look to my right, let's say. Now, what you're doing is clearly that isn't the real world. That's not the real world. It's a hypothetical, what we call counterfactual world. So the question to ask is that hypothetical world where everything is basically the same except for one small thing where you've moved your head to the right, is that new hypothetical world allowed by the laws of physics? Because if it's allowed by the laws of physics, then you can in principle imagine then winding time forward again from this slightly altered initial state And you can, rightly infer that you would have avoided the cyclist and therefore you wouldn't be in hospital and all the rest of it. So the crucial question is, can we kind of fairly, let's say arbitrarily, change initial conditions and still have states of the world which are consistent with the laws of physics? Now, in my book, I give this. Now, you see, sorry, before I come on to that point, I just want to say in most examples in physics, that is possible. So a good example is, weather forecasting. We use what are called classical laws of physics for doing weather forecasting. And by classical laws, I mean like Newton's laws of motion applied to fluids, like the atmosphere is a gas and the oceans are, liquids and so on. And according to those equations, we can change initial conditions very slightly, and the equations don't care, actually. The equations will be quite happy with that slightly altered initial condition. But in the book, I talk about how, and I mentioned it just now, certain models of chaos can exhibit this fractal geometry in a kind of abstract space of solutions, which may not be worth describing in too much detail here. But if you take the view that this geometry is something sort of fundamental, then actually it can tell you that there are certain of these counterfactual states which actually aren't consistent with the underlying laws. So in particular, if you have a state of the world and you add you change it very slightly, but that change takes you into one of the gaps in the fractal, places where there aren't any, where the fractal doesn't exist, if you like, a little gap. If we had a diagram, I could show you, but people can look up, Cantor sets or Mandelbrot sets, and they see, right. They can see these little gaps. There's always gaps. So if this counterfactual world takes you into a gap, then you're no longer allowed to infer that is an allowable state of the world. Now, this may or may not happen at the level of looking for bicycles on pavements or sidewalks, but I do think it's relevant in asking questions about measurements on quantum systems. If I measure, the position of a particle, could I also have measured the momentum of a particle? And here, this idea of kind of gaps in solution space where you can't do these perturbations arbitrarily. So in short, I'm not saying that all counterfactual worlds are impossible. I'm not saying that. But I'm saying certainly in quantum mechanical situations, there may well be counterfactual measurements on quantum systems, which actually are forbidden or at least they're forbidden by my approach to quantum mechanics. And that's a way of getting around this Bell's theorem, which is so important in the interpretation of quantum mechanics. So counterfactuals, in other words, we shouldn't just take counterfactual definiteness for, as a given, that things that we might have done but we didn't do are automatically allowed by the laws of physics. Some are allowed, but some definitely aren't allowed. That's my view, at least.
Okay, I want to talk more about free will, but first on the weather. So when you guys make predictions like there's a 70% chance of rain tomorrow, what you mean is if you ran tomorrow 100 times in your computer models, 70 days it would rain. Now, what if the models were better, like a decade from now or 100 years from now, and you could say, it's 90% chance of rain? isn't that still just a measurement problem? It's an epistemic uncertainty. Or are you saying at some level it'll never be, 100% predictable because of chaos theory and the butterfly effect and things like that?
Well, first of all, you're right that basically in that situation, the uncertainty is epistemic. And you're also right to say that as models improve, computers get bigger, we can make our models more realistic. They can include cloud systems, for example, which current global models can't describe. Then the forecast will get more accurate, and as you say, that will mean that today, when we say there's a 70% chance of rain, for exactly what the reason, sorry, the reason you said that we run an ensemble of say 100 forecasts, and in 70 of them it rains, and in 30 it doesn't. So that gives us our probability. But you're right to say that it could well be in a decade or two, we'll have got that to 90% rather than 70% by improving the models, and just the whole initial conditions will be more accurate. But I do go into the book a bit. There's a kind of an interesting, actually, even non-quantum systems have some strange properties, and I describe quite a lot in one chapter the uncertainty associated with turbulence in fluids, and the weather is kind of like a manifestation of turbulence in the whole atmosphere as a fluid. And in particular, I talk about the work of a meteorologist, American meteorologist called Ed Lorentz, who's pretty much the father of a lot of chaos theory. But he actually wrote a paper in 1969 that's actually less well known than his famous 1963 paper, which was the origin of chaos, which is how does uncertainty grow in a turbulent? So I should say a turbulent fluid. You see, if you look at a turbulent fluid, it's got eddies and whirls, but you can kind of zoom into one of those eddies and you see smaller eddies, and you can zoom into one of those smaller eddies and see yet smaller eddies. So it's actually got a bit of a kind of what we call self-similar structure, like fractals have. So if you look at a weather system from a satellite, and then you zoom in to a bit of the weather system, you see clouds. And if you zoom into the clouds, you'd see turbulence within the clouds. And if you zoomed into the turbulence, you'd see smaller turbulence. Anyway, so Lorentz asked the question: how long would it take for small-scale turbulence to start to affect uncertainty in the very largest weather scales? And there's a really kind of, from a conceptual point of view, there's something very interesting which he uncovered, which we haven't yet been able to prove mathematically whether this is actually true or not, which is that the time for uncertainty in a small-scale piece of turbulence to affect a large-scale piece of turbulence has a fixed time scale, and it doesn't matter how small that uncertainty is in scale. It will take a fixed time, let's say a couple of weeks, to affect the uncertainty in the very largest scale weather system. And this is actually a little bit different, or this is, in fact, is quite different to normal chaos theory, because in normal chaos theory, the idea is that if you could actually reduce the uncertainty to like an infinitesimally small amplitude, you could predict as far ahead as you'd like, because you'd kind of suppress the chaos for as long as you wanted by making the initial uncertainty sufficiently small. But Lorentz conjectured, and with pretty strong mathematical arguments, but they weren't 100% rigorous, that there is a finite time for uncertainty in a turbulent system to grow to larger scales, no matter how small the uncertainty is. Now, if that's correct, it means that although we'll be able to get that, like as you said, 70% to 90% for a weather forecast for, the next few days, we'll probably never be able to predict in detail the weather beyond 2 or 3 weeks. That's just going to be hopeless. Now, the interesting thing is that this Lorentz's conjecture relates to a problem which appeared at the turn of the millennium. So in 2000, the Clay Mathematics Institute published a list of unsolved mathematical problems to kind of parallel what the famous mathematician David Hilbert announced in 1900. He famously gave an address where he said, these are the most important unsolved problems in mathematics in 1900. And the Clay Mathematics Institute, with advice from mathematicians around the world, announced a similar list of problems in 2000. And one of them was essentially this problem of turbulence, solving this uncertainty about how uncertainty in turbulence grows. And I could go on about this. I mean, this is what actually Lorentz meant by the butterfly effect. It's this notion that a tiny scale disturbance could affect something very large in a finite amount of time. So the butterfly effect actually has been slightly misused over the years, and that's what it really means. So there's a lot of fascinating stuff, even in kind of classical physics about uncertainty.
Yeah. So, but the butterfly effect, the flap of a butterfly's wings in the middle of a hurricane isn't going to have any effect at all. It has to be in the very early conditions or when the system is teetering on shifting, kind of a change, what do they call it? A change transition, a point of criticality. I think chaos theorists use that, like drop grains of sand and you get a little pile going, all of a sudden it collapses. And at that moment, the one little grain matters, but most of the time, one little grain doesn't matter. So it depends on the conditions, either early initial conditions or when it's teetering in the balance. So the horseshoe nail doesn't matter for most of the battle, only either early on or if the battle is hanging in the balance.
That's absolutely right. And we talked about my decision to switch fields.
Yeah.
One of the things which I like to think, and people may curse me for it possibly, that I have done, which has sort of had an impact on people's lives, is that I've introduced this notion of probabilistic forecasting using these ensembles, so running models multiple times with slightly different initial conditions and so on. Initially, it wasn't so much people. It's not like my colleagues were trying to think of the right word, sort of skeptical about it, because if you have to run a weather model 50 times for each forecast start date, that takes up a lot of computer time. And what they perhaps didn't like was that they had other ideas on how to use that computer time. They'd rather improve the resolution of the model and so on. And they would say, well, most of the time, we can forecast a few days out pretty well. But I used to show them results from Lorentz's model of chaos. And I said, look, this is a very sort of generic situation that you can have within a single chaotic model, you can have initial conditions that are very predictable, which actually aren't chaotic at all, or they're not for a long time. You have to integrate them out many, long period of time before they start showing evidence of unpredictability. And in the very same model, you can find initial conditions where the uncertainty absolutely explodes from the very start date. And, I said there's no reason why this can't happen for, the real weather. And the problem is if you make blatantly wrong forecasts, people lose confidence in you. And around this time, there was just the most, for me, wonderful example of this, which people of my age who are British will know this because it's kind of etched in our national psyche, if you like. That in 1987, the weather forecaster 16th. Came on the BBC TV, a guy called Michael Fish, everyone knows this. Michael Fish, everyone British knows it, came on TV and said, it's a kind of interesting story, actually. Somebody apparently from France had phoned up to say, they heard somewhere there's a hurricane on the way. Is it true? And he just laughed it off. He said, don't be stupid. We don't have hurricanes in Britain. There'll be no hurricane. Don't worry about that. And then the next morning, there was literally hurricane force winds, hurricane force gusts, and, caused, I guess in today's money, would be many billions of pounds of damage, and people lost their lives, and all sorts of chaos ensued. And the head of the Met Office, there were calls for him to resign. The government, did an inquiry. We spend all this money on the weather forecast service. How could they get it so hopelessly wrong just 12 hours before they didn't know about this thing? So we took a look at this case, and it just is a spectacular example of just kind of explosive unpredictability by introducing tiny, tiny flaps of butterflies' wings, if you like, or computer types of flaps of butterflies' wings. We showed that just within a day or so, the solutions would completely diverge from the most horrendous storms to completely benign weather. And it just made it completely clear then that the only way to sensibly address this issue is to develop an ensemble approach to forecasting where you introduce these small uncertainties. By the way, not only in the initial conditions, but also in the model equations. So we introduce noise, and I have a big chapter in the book about the benefit of adding noise into certain nonlinear systems. And that leads to much more reliable forecasts. And when you can trust the forecast, and when you've got to be careful. And the really exciting thing about all this is that now humanitarian organizations are using this type of information for deciding when they can be proactive in sending aid and medicine and shelter and water and food and so on to areas that are potentially at risk of some extreme weather event. Whereas in the past, with the old-fashioned deterministic forecasts, so where you didn't have any estimate of uncertainty, it was just too risky. They'd run out of money very quickly if every time there was a forecast of an event, they sent aid out, then they just run out of resources immediately. Now what they do is they have a threshold, a probability threshold, and they'd say if the forecast probability exceeds this threshold, then we take precautionary, proactive action. And they've done because now you could do a proper cost loss analysis of whether the uncertainty is large enough. If it's too large, then obviously all you can do is sit and wait and see what happens. But if the uncertainty of this extreme event is sufficiently small, so that the probability of it exceeds the predetermined threshold, then you have a logical and objective reason for going in and helping people ahead of time. And that's always going to be more effective. But it means they make use of their limited resources in a much more kind of objective and way. So I know people curse probability of rain on their apps and so on, and I can understand that. Why don't they just tell us what it's going to be like? But this is a case where actually for really serious extreme weather, this probabilistic approach really is the way to make informed and logical and objective decisions about whether it's sending aid into a region or evacuating a region or whatever it is. And really, that's where weather forecasting is important.
Yeah, I wonder if you could comment on climate change models related to this. You'll often hear from the climate skeptics, well, look, the limitations of these computer models, these guys are running out a couple of days or a week, and then after that, it's random. So how can you say a century from now, this is where we're going to be, therefore we have to take drastic action to cut CO2 gases and so on? What's the difference between those kind of models, and how confident are you that they can make long-term predictions?
Right. Well, there's a number of points there. I think the first point to make is that one shouldn't conflate the weather forecast problem with the climate change problem. And I'll give you a very simple example of what I mean. So I'm in my study in southern England. I'm about 20 miles south of Oxford, and we've had quite a remarkably warm, for Britain anyway, we've had a remarkably warm and dry summer. And today is just another example. I mean, outside the temperature's probably in the high 20s, which is, we actually hit 40 Celsius, which I don't know what that is in Fahrenheit. Well over 100, 110 maybe. I don't know. But look, I can say with complete certainty, I think, 99.999% certainty, that in 6 months' time, so in January, it will not be 29 degrees Celsius, right? And that's because every day the sun, spends a little bit less time in the sky, and we have an annual cycle. So in other words, there's a kind of a predictable astronomical forcing which affects the statistics of weather. Now, I can't say in 6 months' time whether it'll be rainy or dry, but I can say pretty clearly it's going to be colder than it is today. And climate change is like that. With the predictable atmospheric forcing of the annual cycle is now replaced with a predictable increase in greenhouse gas concentrations in the atmosphere caused by our emissions. So we can say, I think, with pretty much certainty that because most of the governments of the world have said we will not be reducing our emissions to zero until at least mid-century. So we can say that we will continue to emit carbon dioxide into the atmosphere for at least another, say, 50 years, possibly more. And as a result of that, carbon dioxide concentrations will increase year on year for at least the next 50 years, possibly more. And that has a predictable effect on the statistics of weather, just as the seasonal cycle has a predictable effect on the statistics of weather. So it's just a kind of a class error to say, oh, well, because we can't forecast the detailed evolution of weather beyond a couple of weeks or so, it's hopeless saying anything about climate change 100 years from now. You're just conflating two completely different types of problem. One is an initial condition problem, the weather forecasting, and the other is where you're adding a kind of an external forcing. So what can we say? Well, so there is no doubt whatsoever that as a result of this increase in CO2, the global temperatures will continue to increase. Now, as I discuss in my book, how much they will increase depends on factors which actually are uncertain. And perhaps the biggest uncertainty of all is due to clouds. Clouds have different effects on the climate. They have many effects on climate, but they have different effects on the surface temperature of the Earth, depending on what type of cloud they are. So when you have this kind of what are called stratus clouds, very low level, sort of thick clouds which just block the sun, then that cools. I mean, then the atmosphere is typically colder than if the clouds weren't there, because basically the sun is reflected, the sunlight's reflected back to space. So the clouds just block the sun, cool the surface. On the other hand, when you have very thin cirrus clouds, which are way up in the high atmosphere, 10 kilometers or more up, and they tend to be much thinner clouds and often just made of little ice crystals. They actually play a much more of a role in trapping the heat from the surface of the Earth and stopping it radiating out to space, which is why quite often, certainly in Britain, when you think there's going to be an overnight frost and then a layer of cirrus cloud comes along during the night, that can often stop frost from forming because you actually end up warming the planet. Well, in the sense of the atmosphere loses less heat to space.
So this would be the greenhouse
So
effect
the critical question, a really big, like zeroth order question for climate change is what are clouds going to do? Because if cirrus clouds increase and stratus clouds decrease, then this will amplify the climate change signal. It'll make it warmer, potentially by quite a lot. That's actually then you're into catastrophe, like catastrophic changes in climate change. If stratus clouds, low level kind of stratus cumulus clouds, dissipate, and the higher level clouds either stay the same or increase. If it's the other way round, then actually clouds will help us. It won't be quite as bad. Unfortunately, the models are tending towards the wrong way. They're making the low-level clouds less of them, and that's amplifying the warming. But I would say because we can't represent clouds explicitly in models, they're done with very simplified formulae. This is the biggest area of uncertainty. Now, the other area of uncertainty is what happens at a regional level. So are we going to get more droughts? Like here in the UK, we've had a drought this summer, and the question is, this drought may well continue into the autumn and winter, and that's a really big question for infrastructure. How much more reservoir capacity do we need? Is based around this question of how are long-lived droughts of multi-season droughts becoming more commonplace or not under climate change. And current generation models just can't answer that question because they're not good enough at simulating these long-lived droughts. And that's because we can't put enough resolution into the models, and that's because the computers resources we have are not big enough. So I've been advocating for a CERN for climate change, where we pool our resources and just build buy the biggest. We now can buy what's called exascale computers, 10 to the 18 floating point operations per second. That's a million calculations per second. That will make a big change in our ability to simulate climate change accurately. We could have one of these centers in a place where the energy comes from renewable, could be solar, wind, or geothermal or something. We don't want to burn coal to run a computer, that's for sure. But we can do it with renewables. And if we form a new international institute, this could make a big advance in our ability to understand and again reduce these uncertainties in future climate change.
Would that be a good solution also for predicting pandemics and economic recessions? Since you mentioned those and you have chapters on those.
Well, it's an interesting, just coming back to my story about Michael Fish. Here was a situation where the weather, actually most of 1987, I don't think the weather was especially unpredictable or something, but suddenly in October 87, along this came this kind of a massively unpredictable storm. What it demonstrates is that what I said about the Lorentz chaos model, that the model itself is chaos, but the degree of chaos is not the same day in, day out. Different initial conditions have different degrees of chaos. And there are some initial conditions that are exceptionally unpredictable, and other initial conditions are reasonably predictable. And in fact, you could say most of the time for these chaotic models, the initial conditions are reasonably predictable, but just there's this small region where they're exceptionally unpredictable. Now, you look at other systems like the economy, or global health, or indeed the state of conflict in the world, where you could say for a lot of the time things we sort of bump along in a reasonably kind of predictable and sort of stable way. But occasionally we get these, like the 2008 financial crash, and then of course in terms of public health, the COVID pandemic, and now we have the Putin's invasion of Ukraine has kind of triggered a global crisis. So it does seem that there are clearly parallels with other types of systems, perhaps more involved in social sciences. So I do discuss in the book, because I did a bit of research contacting economists and epidemiologists and conflict modelers to see to what extent ensemble-based forecasting is being used in these other fields. And I think the answer is they're much less well developed than in sort of weather and climate. But perhaps the one where I did find the most kind of traction was actually in COVID modeling, and in particular in the United States, where a number of university groups have developed their own individual COVID models. But there was a central facility which took in all of the data from all these different models and synthesized it in a kind of probabilistic way, and showed actually that the ensemble forecast information of COVID, things like COVID incidents and COVID hospitalizations and so on, was actually much more skillful from the ensemble as a whole than from any one of the models. And that got me thinking, by the way, that just as the World Meteorological Organization, WMO, has been sort of leading the development of climate change prediction ensembles, which go into these IPCC assessment reports, the Intergovernmental Panel on Climate Change. So the WHO, World Health Organization, could maybe mastermind some of these ensembles for doing much more kind of coordinated disease prediction in, not only COVID, but all the other types of important diseases around the world. I think they probably are starting to do this, but I think there's a lot that they can learn, as indeed the economists, I think, and the conflict modelers, from what we have been through in weather and climate prediction in the last few decades.
Yeah. I think one of the problems with the divisiveness politically, particularly around climate change, pandemics, economic recessions, is the amount of doubt that arises amongst people who just kind of watch the daily news go by, and Dr. Fauci says this, now he says that, the CDC recommended this, now they recommend that, they can't keep their story straight, I should just be skeptical across the board. This is kind of a larger question, what is a skeptic? Are you a climate change skeptic, or are you skeptical of the climate change skeptics, which would make you a believer, whatever that would mean in science? You see what I'm getting at? Why should people trust what health experts say about the coming pandemic, or what we should do? Wear masks, don't wear masks, get the vaccine, don't, whatever. How do you think about it on that larger scale? And what would you recommend to people who bring these kinds of things up, which sound reasonable? Like, they keep changing their mind, and they've been wrong so many times. Why should I listen to the experts now?
Well, I would say if I could take climate change as an example about which I know the most, so let me stick to that because I think what I'm talking about. You see, you have to realize that there are two sides to the issue. There's a scientific question, And then because we're talking about policy relevant science, there is a political, if you like, analysis and decision that has to be made using as input the scientific evidence. So in the case of climate change, I think this is true of most, not necessarily all, but most of my colleagues. They have tried to address this question of climate change from a science point of view. So what does that mean? It means if you ask the question, are humans emitting, by burning fossil fuels, are we emitting carbon into the atmosphere, carbon dioxide into the atmosphere? Yes, there's no question. Scientifically, there's no question about it. Is that warming the planet? Yes, there's no question about that. Will the planet continue to warm by our ongoing emissions of carbon dioxide? Yes, there's no doubt about that. Are we increasing the risk of, severe or extreme weather events by these emissions of carbon dioxide? Yes, there's no doubt about that. Should we therefore cut our emissions of carbon dioxide? Now, once you ask that question, you're no longer asking a science question, you're asking a policy question. And as I say, I think I speak for a lot of my colleagues. They would just say, well, that I can give you my personal view as a human being on the planet. But if you ask me from a science point of view, should you cut emissions, then I can't tell you because that involves value judgments. There is a cost to cutting our emissions. We do, everything in daily life, hospitals and, social welfare, everything, is currently geared around fossil fuel energy. Everything, in our lives currently is based around fossil fuel energy. So converting to zero carbon energy is difficult and involves a cost. And you could argue, for example, and I have some sympathy with this argument, that in the developing world, where we want people's standards of living to get, close to our own in the rich world, if we suddenly say stop burning fossil fuels and only use solar panels, we're going to hinder their economic growth. So if you try to make that final step of should we cut our emissions, you're going, into politics. And I think it's important to realize that that is where scientists have no bigger or better insights than anybody else. I know pretty well what a molecule of carbon dioxide does in the atmosphere, but trying to, estimate way up on the one side the benefits and on the other side the costs of moving to zero carbon involves, economic, social assessments that I'm not an expert in. In the book, I try to give an approach to that based on what's called an estimate of a value of a human life. But, I don't have any, I don't consider myself an expert at that. So what I'm trying to say here is that perhaps if we take COVID as an example, the politicians, the scientists would have gone to meetings with the politicians and said, well, these are what the models show, and maybe not at the beginning of COVID, but certainly towards the end, they were able to show their results in a probabilistic way. So this is the probability that there will be X deaths per 1,000 people or something like that. Then the politicians have to decide, is that risk high enough to take action to shut down an economy or to stop people moving around? And when people say, oh, well, they got that wrong, it wasn't, the decisions may or may not have been wrong, but it wasn't the science that was wrong. It was maybe in hindsight the decision that was made wasn't the right decision. I don't know. But actually, at the time, maybe it was the right decision given the evidence. But I just want to emphasize that point that there are, saying, oh, they got it wrong. You may actually, or the people making that statement, may be more referring to the decisions that were made on the basis of the evidence that there was at the time. It's like if I say to you, there's a 70% chance of it raining tomorrow, you might say, well, in that case, I'll take my umbrella to work or to wherever I'm going. And then, of course, it may not rain. So does that mean you were wrong in deciding to take your umbrella to work? I mean, the fact of the matter is, at the time, the best available evidence was that there was a 70% chance it would rain. So you have to recognize that when you make decisions under uncertainty, I don't think actually calling them wrong is the right way to describe such a decision. But the uncertain, in hindsight, it may be that a different decision would have cost you less. But this is just an inevitable consequence of uncertainty, and it's better than just tossing a coin in the air when you're making a decision where that's an important. I mean, taking an umbrella is not an important decision, but if it's whether to evacuate somewhere or something like that, then having the best scientific available evidence is better than just, tossing a coin.
Yeah. People get confused about that, like with the 2016 election of Trump and Clinton. That Hillary had a 70% chance of winning. Well, then how did Trump win? Well, if you ran the election 100 times, Hillary wins 70 of them. So this was one of the 30. And that's how it happens.
Right.
So, all right. So let's go back to...
And I think it's important for, scientists to be honest. I mean, I tell you what the hardest thing is for me, and I'm sure it's true of when you get interviewed by a journalist who's writing a story for, tomorrow's edition. You could tell that he or she wants you to be more definite than you are, because it's not a great story if it's couched in the language of uncertainty. So you're kind of feeling under pressure the whole time to be more certain than you are. But I think it is important for scientists to tell, to be honest about uncertainty. And ultimately, that's the politicians' jobs to make decisions under uncertainty. That's why we vote for them. It's not for scientists to make those decisions for them. So we shouldn't, let them off the hook. They have to it's tough, sometimes it's tough making decisions under uncertainty, but the scientist's job is to tell them the evidence fairly and dispassionately. And that's what I certainly try to do. And that's the kind of philosophy in the book, if you like.
Yeah. Carl Sagan had a funny story about that, how he would give some rough estimate, like, I don't know, it's about 150,000 kilometers to whatever. And then the journalist would translate that into the archaic American standard system, and it would come out, at some exact number, like 0.67. How did he know that it's exactly that? It's like, he doesn't. It was just a rough estimate in the first place.
Right. Yeah.
So,
that's right.
All right,
Yeah.
Tim, let's just kind of wrap up here by going to your last chapter, and again, return to free will, consciousness, and then God, which I love all that stuff. So just one final point on the free will issue. I'm a compatibilist. I liked your approach, and it gels with mine very much. I think we can do otherwise. The universe is not predetermined. We are part of the causal net, determining things ourselves, as well as aware of the factors that we can at least try to control. Now here, the determinists would say, no. You're just confusing different levels of causality. So here I'll use Adrian Rain's examples from his book, The Anatomy of Violence, about Mr. O.F.T. Oft. They don't use his real name, but he was this school teacher who turned out he had an orbital frontal cortex tumor, and he, at mid-age, like 40-something, became kind of a pedophile. He started acting inappropriately with his wife's daughter, his stepdaughter, and kiddie porn on his computer and all this stuff. So she turns him into protective services, and he's going to go to jail. And then the psychiatrist scans his brain, and oh my God, he's got a tumor there. And then, so the way Rain presents this, it's like you kind of feel sorry for him, like, oh, he's not a pedophile. He's a medical patient. He has this tumor. And, they took the tumor out, and those feelings go away. He's back to normal. And then 6 months later, the wife finds more kiddie porn on his computer. Oh, so brain scan, it's back. So you know, there it's obvious. And then Rain's second example is this African American young man named Dante Page, who was convicted for raping and murdering a college age woman in Colorado, and he was up for the death penalty. And Rain was on the defense team's attempt to get him life in prison rather than the death penalty. So he wrote extensively about this guy's background, which is the most horrible background you could possibly imagine. You know, single mom who's addicted to drugs, beaten constantly by the men in her life, dropped on his head a dozen times, many trips to the ER for brain damage and so on. By the time he's 18, he's had like the worst life anybody could have in America. Just horrible environment and gangs, terrible diet, you name it, he's got it. Now, Rain's point is that there's nothing on the brain scan really quite like a tumor. You know, but it's tumors all the way down. It's the equivalent of, you just don't see what the neural changes are because of that horrible background, but it's the same thing. So why is the Dante Page different from the pedophile guy with the tumor? And the determinists would say it's all the same. They're all just physical causes. The brain is a physical mechanism that obeys the laws of physics and everything else. And so how would you respond to kind of a deterministic argument like that?
Yeah, I mean, I certainly accept that, you know, there are situations where the moral culpability of somebody is borderline because of medical conditions. But look, let's just take Hitler. I mean, surely we can all agree that Hitler was evil. You know, he exterminated or attempted to exterminate, you know, large sections of society. What word can you use than evil? So the argument that, you know, and I understand the reason why people don't like determinism is that they say, oh, well, you know, it was all conditioned by whatever the cosmological, you know, Big Bang initial conditions were. That sort of set the clock ticking, and then everything after that was inevitable. So we can't kind of blame Hitler for what he did because it was all determined by the initial conditions. So that's, I think, probably the most common type of argument that people who don't like determinism bring up. And I actually find that a powerful argument. You see, so it's kind of, you know, at the level of physics, at theoretical physics, determinism, I think, is quite an attractive concept, because the alternative, which is indeterminism and God playing dice and things, is just such kind of nonsense, it seems to me. But when you phrase it in this moral way, moral capability, it's a dilemma, because, you know, nobody wants to let Hitler off the hook for what he did to the Jews and the Gypsies and everything else. So how do we square that? And I tried to address that again in the last chapter by coming back to this notion of a fractal attractor, this idea that, which in some sense borrows a lot of ideas from Einstein, that the laws of physics are geometric. So his idea about general relativity was that the laws of gravitation are ultimately caused or due to the fact that space-time has a sort of non-trivial geometry. And these fractal geometries in the space of solutions of the equations is another kind of geometric approach. And what it does is, if you take that view, then actually the initial conditions, the cosmological initial conditions, are no longer somehow fundamental and sort of the moment that everything takes off from. In some sense, all of the states of the world, from the cosmological state to the present day and in the future and so on, are sort of have equal ontological status as points on this geometry. And what that does then is to tell you that there's a kind of it's almost like a self-referential picture that you have, the geometry is sort of telling us how we evolve from one day to the next. But equally, what we do is determining the structure of this geometry. There's a kind of duality here, which is kind of a little bit difficult to say exactly. I mean, I don't have a precise way of defining it, but there's a sort of duality here between the geometry. It's a little bit like in general relativity. There's, I think, John Wheeler, the famous theoretical physicist, kind of said, the geometry tells matter how to move, and the matter tells space-time how to curve. So this is kind of duality in terms of space-time geometry. And I think there's something in parallel going on here, that the space-time, that this fractal geometry is in some sense telling us how the atoms in our body are going to evolve from one day to the next. But our actions equally, in some sense, determine the structure of this geometry. Again, there's a sort of duality. I'm shaking my head because I don't have a clear enough picture to kind of really nail down what I'm saying here, but I feel it intuitively that, as with the Wheeler duality for space-time, there's something here. But what that would mean is that then will not let Hitler off the hook, because it does put some onus on what we do, as means we have to take responsibility for what we do. I throw this out in the last chapter. Look, I mean, the book, it's important to make this point, that the book starts very solid, the maths and physics of chaos. It goes through things like weather and climate, which again, pretty damn solid, I would say. Talks a bit about economics, COVID and something, perhaps a little bit more uncertain there. The last section of the book is all about consciousness, free will, moral responsibility, and then, as you say, right at the end, God. And I think I tried to say right at the beginning of that section, this is much more speculative. So I can't sort of absolutely nail everything to the mast and say I've completely clicked this. But there's something, I think, important here about taking away the Big Bang as something where, everything was set in stone at the moment of the Big Bang and nothing could change, to something much more fluid, I suppose, in some sense, where we do actually have some role in determining this geometry, just as the geometry has a role in influencing us. So I think this, at the very least, let's say this, it provides a new ingredient, I suppose, into the debate about determinism and moral responsibility and so on. And I hope at least that will get people thinking.
Yeah, no, I like that very much. All right, last page here, you talk about, for example, in the cosmological invariant set model, there is an afterlife. We and our loved ones will be coming back in future epochs of the universe on trajectories in state, space, close to the present one, but none precisely the same as the present one. What in the world are you talking about there?
Well, yeah. So if you take something like the Lorentz Model, the states in the Lorentz Model, they evolve on this fractal geometry, and they can go round and round and round and then come back. They never come back exactly to where they were, but they come back very close. There's a point, in the future of a trajectory in this solution space. I call it state space. I try to explain what I mean by state space in the book, but there's no time here to kind of go in detail. But let's say space of solutions, where the solution comes round. It never exactly comes back to the point you started, but it comes as close as you like. And at that moment, that state is like within the flap of a butterfly's wings away from that original state. So if this is how the universe works, and that's my belief, actually, and it links in with a lot of Roger Penrose's latest ideas about what he calls cyclic cosmology. But with this difference, that the universe is never cyclic in a precise way. It doesn't actually repeat itself, but it gets back to a state which is very close to where it was in a previous eon. And so what that means is that it's a bit like actually the example we had earlier of me walking out of the shop and being hit by a bicycle. In a future eon, I will walk out of that shop and see the bicycle and avoid it, and I won't end up in hospital. So certain things will be better, but maybe some good decisions, that I made, I'll make lousy decisions. And so in other respects, it'll be worse. But that's what seems to be, I'm being speculative, I understand all that. But if you take this model of the universe as a chaotic system evolving on one of its fractal attractors, as they're called, this is where it leads you to a universe where, in some sense, you do come back, but things are slightly different, and I find that quite. So, as I say, loved ones, you'll meet loved ones again, if that's right. But you'll have a different life with them. Things will be different.
This would make God something of a computer modeler who is replicating our loved ones in some sort of virtual reality, or am I missing that? It's something different in the future.
Well, it wouldn't be a computer, actually, because the thing about computers is because they're, one of the things about if you have a model of chaos and you represent it on a computer, then actually the state does eventually return to exactly its starting point, because the numbers inside a computer can only be represented with a finite number of bits. So God isn't a computer, but certainly God is mathematical in some sense. I just finish, I don't know whether this is giving too much away, but I finish with this conjecture. Well, suppose God just is this geometry in some sense, this fractal. I mean, that is God. It's kind of a Spinozian philosophy of God, but sort of on steroids, because it's not just our universe, but it's like the sum totality of all of the eons and stuff put together. And I kind of, it just amuses me that Lorentz, who invented the butterfly effect, which we spoke about, he also invented this model of chaos. And if you look at the attractor of the Lorentz model, it actually looks like a butterfly. A bit of the wing of that butterfly is on the front cover of the book. It looks like a butterfly. Now that is a complete, I mean, you've got the sort of two wings of the butterfly there, sort of thing. But that's a complete coincidence. It's totally, it's just fortuitous. But it just got me thinking, maybe the geometry of this cosmological attractor is a picture of God. I mean, who knows?
But this isn't a personal God.
I just feel it's worth exploring, but who knows?
Yeah. Well, at this point, that's all you can do, because I do think we kind of hit an epistemological wall when we talk about things like that, or why is there something rather than nothing? Well, what do you mean by nothing? And then you get into the physics and metaphysics of nothingness, and then it's just like, words become...
I do have... Yeah, I do... I'm not somebody that dismisses religion and God out of hand, which of course a lot of scientists do. And I think, we need to look for ways of reconciling science and religion in ways which are not, as confrontational as they often are. And this is just my attempt to raise a concept which might possibly bring people together in a way. Do
you mean as a strategy for, can't we all just get along? Yes, that would be good. Yeah. Versus an actual epistemological attempt to understand the nature of reality. We need religious people and their views as well as scientists.
Well, I'm not sure what I'm saying. I mean, you need... can I say? I think to make progress in fundamental science, you do, it's not, science is not a kind of a logical process. You need insights of leaps of imagination, which often you don't get from just staring at equations. It's having some more kind of liberating philosophy which can take you to places that you just don't get by looking at equations. I think often that is important in science. Progress is kind of inductive, it's not deductive. And people with religious feelings and backgrounds, I think there are useful, they have insights that could be useful. I mean, I can't say categorically that they are needed, but on the other hand, I would feel science would be the poorer if we somehow excluded such people. I think it would limit us in our ability to think outside the box, which we do need, unquestionably. And in this area of quantum gravity, we need, unquestionably. So I'm trying to say that in physics, at least, being cognizant of different religious, philosophical traditions, I think can be useful. Yeah.
That's right, because you had a discussion on the relationship of noise in the brain and creativity, if I'm remembering that right. So this would be an example of we need as many people as possible who have thought about these big questions, because who knows what noise goes on in their head, and they come up with some ideas related to spiritual traditions or whatever that are useful.
Right. That's right. I mean, I as you say, it comes back to this question of what's so special about 20 watts of power that will run the brain. And one of the things that's special about it is that there likely are situations where the signals in the neurons are affected by noise, thermal noise, maybe actually even quantum mechanical noise. Now, what manifestations would that take? Well, it could be that that's what helps us bring ideas together from what would be, in a purely sort of logical, deductive way, unlikely connections. And so you need two ingredients to make the connections. You need two ingredients. You need to have those ideas. You need to have the ideas don't come out of nowhere, but you need to have had those ideas. And then the noise, which, by the way, happens mostly, susceptibility to noise happens mostly when you're in a very relaxed mode, not thinking about anything in particular. That's when the brain can make connections between really quite different ideas. And I discuss in my book how the eureka moments that some of our top, Nobel Prize winners have had, these have all occurred when they're just relaxing, doing nothing. And I tell my students, don't spend the whole day in front of the computer and night in front of the computer, because you're just, you're preventing the eureka moments from happening. So the brain, I think, so having a diverse kind of multi-dimensional view of the world from different perspectives, and then that ability to relax and allow the noise in the brain to make the connections, that's the kind of, in my view, the secret to creativity and inventiveness.
So here we'd probably say noise favors the prepared mind. Because if I have a dream about riding on a beam of light or falling down an elevator shaft, I'm not coming up with the theory of relativity, because I'm a nobody in physics, right? You got to have the mind ready to solve the problem.
You have to have a certain amount of, you have to remember, Einstein was not a mathematical genius. His knowledge of mathematics was actually somewhat limited. By the standards of mathematicians, people wouldn't have called him a mathematician. But he knew enough mathematics to realize, when he'd had that idea about riding a beam of light, that had mathematical implications. And then he went to his friends Minkowski and so on, and then formulated things mathematically. So you don't need to be like super expert, in different areas, but you do have to have a general broad I think, knowledge of different things. I think that is important. At least and that squares with my own experience. I've tried to, know a little about a lot of things, and sometimes that can be useful.
Yeah. One of my favorite Steve Gould essays was talking about, since we started with Feynman, we can end with Feynman, where he was going to Caltech to give a public talk, and so he was contacted by Feynman's office. Would like to have lunch. Yeah, okay, wow, the great Feynman. Yeah, that'd be great. So Feynman proceeds to bounce some ideas he had about evolution with Gould, which essentially turned out to be sexual selection, which Darwin had figured out by the 1870s. That it wasn't just natural selection, there was sexual selection, females selecting males, for example. So they're competing and they have different kinds of camouflage or whatever colors that would not be camouflaged if it was natural selection and so on. Anyway, Gould finally said, well, yeah, we worked all that out like a century ago. and Feynman said, I never read anything about a subject like that because I want to come to it fresh with a clear mind. Anyway, Gould's point of his essay was, yeah, except it's good to know what's already been done in case, the errors that you're about to make have already been made and we figured those out.
That's right. I agree.
So, all right, Tim, well, you've been very patient. We've got almost 2 hours here, and I appreciate you entertaining all my questions here. Standing in for our listeners who don't know much about this stuff, I think your book is super clear. I hope everybody reads it because it's just a masterful example of clear science writing on some of the biggest, most interesting, important topics of our time. So thank you for doing that. What's next on your writing or research plate?
I'm writing a paper whose title is Quantum Physics from Number Theory. So
okay.
I'm a great believer that, Newton discovered the calculus, and the calculus is used in pretty much all of modern physics, from, throwing a stone in the air, forecasting the weather. Even the Schrödinger equation in quantum mechanics is based on the calculus. The problem with the calculus is that it assumes variables are infinitely, variable, whereas number theory is about the properties of whole numbers, 1, 2, 3, 4, 5, 6. And very little is made use of number theory in physics, and certainly in fundamental physics. So my project at the moment is writing a technical paper on how some very interesting kind of number theorems about properties of whole numbers, the relationship of whole numbers and what are called trigonometric functions, like the sine and cosine of an angle, could provide some really big insights into the nature of quantum physics. So we'll see how that goes.
And do you get those insights from playing the banjo and guitar, if I can comment on your backdrop? Is that one of your creative outlets? Einstein had the violin, you have the guitar.
Yeah, I play in a village rock and roll band.
Oh my God, that's so cool!
And I've been a folk musician since I was about 12 or so, inspired by the Beatles, I have to say, originally. I don't find much connection between science and playing musical instruments. I'm not somebody that loves Bach because of its mathematical intricacies. I like playing fairly simple music just as an emotional release. There's nothing better than playing Johnny Be Good on a Gibson ES-335 in front of 100 people who are dancing like mad. There's just nothing to compare with it. It's fantastic. It's almost as good as doing science.
I was watching a YouTube video of Queen performing in, I don't know where it was, but there must have been 100,000 people. And there was Brian May. Doesn't he have a PhD in astrophysics or something like that? Yeah. Anyway, I just can only imagine what that must be like. I have a story about
Brian May. He finished his PhD at Imperial College after Freddie Mercury had died and the group had sort of gone into abeyance, and he finished his PhD. And he had to give a seminar in the physics department on his PhD work. And I wasn't there, but apparently he said, I thought this was great. He said, I've given concerts in front of 100,000 people in stadiums. I've played on the roof of Buckingham Palace, in front of royalty and things. I've never been as nervous as I am now giving a seminar in front of 20 people in the physics department.
That's a
which I can
story.
understand.
That's a great story. Every guy wants to be a rock star. And so what do rock stars want to be? I don't know. I guess astrophysicist or something. That's really funny.
Maybe.
All right, Tim. Thank you so much.